Okay, so for this section, 15.4, what we're going to do is we're going to go look at some applications of double integrals. This is going to feel somewhat familiar because we're really just going back to look at section, I think it was 8.4, where we did centers of mass, moments about the y-axis, moments about the x-axis. Well, one of the assumptions that we made in that section was that the density of my lamina was constant. So now we're going to talk about, well, what if I don't have a constant density? Meaning I have some surface or some flat disk, some lamina, but it's not a consistent density all the way through. I'm going to have some function, rho. This is rho. That tells me what my density is at a certain point. So I'd like to know what is the total mass of my lumina. So let's see. The first thing I want to do is if I wanted to approximate the mass, I would take my shape and cut it into rectangles. And I would look at a certain rectangle. We'll have some point in it, right? So for that rectangle, its density is going to be given by x, y, times that area. So then that would tell me the mass of that rectangle, or that little region here. And then I would do that for each one of these. Noticing that if my point that I'm picking is not inside my surface, or on my surface, then that's just going to be 0. So by taking all these approximations, I'm approximating the mass of each one of these rectangles and adding them together. That'll give me a I'm going to take I from, say, 1 to m, and j will go from 1 to n. It's going to give me an approximation for the mass of the lamina. To get a better approximation, I would want to make the rectangle smaller, right? So the number here, m, the number of sections that I break it up on the x-axis, I would like that to be larger. And then n, the number of sections I break up on the y-axis, I would like that to be bigger. What I would really like is for both of those to go to infinity. So if I take this approximation, I can take the limit as both m and n go to infinity. Of rho, my density function, and this will tell me the actual mass. But now this should look familiar from the beginning of this chapter at 15.1. That's how we defined a double integral. So here, this is going to turn into my mass will be the double integral over my region, the region being defined by whatever my lamina is, of rho, the density function, dA. So mass really is just a double integral of my density function. This should make sense because over my region here that we're talking about, let's relate this back to what we did in 15.1 and 15.2. Over this region, I'm saying that I have a different density, which I would think of as a different height. So first we said, well, the volume under some surface. Now I'm just thinking of the height as the density at that point. So to add up all the different densities to find the total mass, I'm just going to do the same thing that we did when we calculated volume. Okay, so let me pause this and rewrite the board for a second, and then we'll talk about moments and center of mass and a moment of inertia. Okay, so I rewrote a little bit on the board here. I still have the same density function for my lamina. The diagram stayed the same. This was the mass formula we just talked about. What I'm going to do now is we're going to talk about moments about the y-axis and moments about the x-axis. So if you remember back from Calc 2, the idea of the moment about an axis is I'm looking at depending on how far away from the axis I am, that distance times whatever mass is at that point, because that's what's giving me the leverage. That's how much I have effectively pushing down at that point. So I'm interested in the mass and the distance away from the axis. So here, if I'm going to talk about the moment about the y-axis, we're going to look back at our approximations here. I'm going to interested in what is this distance here. So for each of these rectangles, that's going to be my x value. And then I want to multiply that by the density at that point. Or the mass at that point, excuse me. So for this rectangle, I would use the distance away from the y-axis, which is my x value. And then I'm going to use the mass of that rectangle. So we said the mass was the density function times the area that I'm counting for. So now to make an approximation for the moment about the whole region, the whole lamina, I would sum these. 1 to m, 1 to n. That's the same setup that we had before, because I want to add up the approximation for every square or every rectangle that's covering my lamina. So then that would give me an approximation for my moment about the y-axis. To get the actual moment, I'm going to take the limit as m and n go to infinity. So what that does here, that gives me a double integral. So my moment about the y-axis is going to be equal to the double integral over my region, x times my density function. Similarly, my moment about my x-axis, what I'm going to do now is I'm looking at, well, what's the distance away from the x-axis? So that's going to measure up this way. So now that's my y value. So here, my moment about x, I could write out this similar approximation, but now instead of an x value here, I'm going to have a y value, because the moments about the x-axis, that distance away is measured by y. So the moment about x is going to be equal to that double integral over my region R. And now it's going to be y rho of xy. Yeah. So that gives me my two moments. Let me pause again. Okay, I hope this pause and start for the recording isn't weird. All I did is I erased the board and I moved my two formulas that we talked about, the moment of y and the moment of x, off here over to the side to look at them, because now I need to talk about center of mass. So for the center of mass, what the idea was, again, revisiting from Calc 2, is that this is the point, there's going to be some point on my lamina here. Let's just make this up. Some point where the whole disk or the lamina with all these varying weights, densities, the masses and everything, it would balance. So I would be able to take my lamina and balance it at that point. The way we figure out the center of mass is I'm going to look at, it's going to be some point, we'll call it x bar, y bar, where x bar is equal to the moment divided by the mass. And y bar is equal to my moment divided by the mass. So what that's going to do is that's going to give me with the formulas that we had earlier. So the top one, mass, is the m. This will give me a way for my lamina to find the point that it would balance on. That if I were to hold it up just at that point, nothing would change. So this is a double integral over the region of x rho of xy over the region of just rho of xy. Keep in mind you have to calculate both of these integrals. I can't just cancel things out and get left with an x value. Okay. So typically, if you're doing this, what you're going to do is you're going to calculate the mass first. kind of in the order that we derive these. You'll find the mass of everything, you'll find your moment about the y-axis, the moment about your x-axis, and then you'll make fractions afterwards at the end to find out what the center of mass is. Okay. The only other thing that we're going to talk about in this section is what's called a moment of inertia. This is used in physics to talk about rotational energy. The idea here is I have my mass, and now I'm going to multiply it by, instead of just the distance away from my axis, I'm looking at the distance squared. Okay, so I'm going to take the same actual formulas that I have for the moments about x and moments of y, and I'm just going to write them with an x squared and a y squared. So we'll go through and we'll do a couple practice problems with these. I'll do one problem that has a mass, one problem that has moments and a center of mass, and then one problem that's dealing with inertias. Okay. Please keep in mind if you have questions, discussion board is a great place to put them, or send me emails. Thank you much.